Hello, I am Aniruddh and this is my video presentation for the project Automating RF Circuit Synthesis. This is a part of my EE4902 mini project under Professor Aniruddhan for this semester, that is Jan-May 2024 semester. Motivation. The role of a designer. Analog circuits play an important role in processing real-world signals and interfacing them with digital signal processing units. The design of analog circuits is challenging as the parameters of the analog circuits are interrelated and difficult to tune to achieve the desired performance. Optimizing one parameter can result in the degradation of another. Designers are always trying to achieve an optimum trade-off between the performance metrics. Analog circuits have nonlinearities associated with their components, hence the final optimum design of a circuit takes a large number of iterations for the fine-tuning of circuit parameters. What is the advantage of ML in this? With the advent of ML in almost every field, it has become all the more easy to automate the circuit design procedure and would give a competitive advantage to the designer. Why this project? This project specifically aims at bridging this gap. The huge amount of time between the picking of the right schematic and the final design can effectively be shortened by automating the process. Typically, this time is estimated to be about 2 months without automation and can possibly be reduced to a couple of days thanks to automation. These are the key motivating factors behind taking up this project. Now, I'll briefly describe the algorithm used. The first step is to select the particular topology that will be automated. In this project, I have worked on two topologies. The first one being the noise cancelling LNA, low noise amplifier, and the second one being the resistive feedback LNA. The second step being design the schematic in cadence. The third step being select the operating point. The local minima is highly influenced by the operating point chosen. The operating point is chosen such that the input impedance looking from the input port is set to around 50 ohm. This highly influences the S11 spec. Moving forward, you need to extract out the netlist. The next step is to run the code corresponding to that particular netlist. By running the code specific to the netlist, I mean to say that the gradients need to be specified in accordance to a particular topology. Next, you need to pick a certain hyperparameter that sets the threshold of the loss below which you would term a netlist to be good. And if a netlist satisfies the loss being less than this particular threshold, we would run the sensitivity and PVT analysis on these netlists. The mismatch is also accounted for in this analysis, in the PVT analysis. And then the final step is to pick the netlist that satisfies all these constraints on the loss, the sensitivity and the PVT variations also mismatch, and then you would term this the best netlist. Now I'll briefly describe about gradient descent. Gradient descent is an optimization algorithm that mostly converges to the local minima. It works as follows. You pick a starting point and then you move in the direction of the steepest gradient at that point, and that is done with this equation. Wj goes like Wj minus eta times dV by dW of loss. So basically this term, as I am showing, indicates the direction of the steepest gradient, and this eta is termed the learning rate. The loss or objective function used in this project is as follows. We use the ReLU activation function. The ReLU activation function is defined as max of x comma 0. That is, it takes the value of x if x is greater than 0, and it takes the value 0 if x is less than 0. And I'll describe the loss now. So the gain loss is defined as ReLU gain specification minus gain simulated. For example, if the gain simulated is higher than the gain specification, this argument goes less than 0 and the gain loss is 0. Why does this make sense? This makes sense because if your gain simulated is higher than the gain spec, you have already met the gain spec, so you should not be contributing any gain loss to the final loss term. Similarly, the IIP3 loss is defined as ReLU, IIP3 specification minus IIP3 simulated. This is also correct, because if your IIP3 is above the specification, you are doing much better, so you need not do anything. Similarly, we define the S11 loss as S11 simulation minus S11 specification. That is, if your S11 simulation is much less than the S11 specification, your input port has been matched very well, so you are performing better, so that should not contribute to any loss, which is making sense here. Similarly, IDD loss, that is the DC current drawn from the power supply, is given by IDD simulation minus IDD specification. The same goes with the noise figure, and the overall loss is given as a linear combination of gain loss, IIP3 loss, noise figure loss, S11 loss and IDD loss. And here by definition the IDD specification is set to 0. This is just a matter of convention, and depending on the use case, the values of alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 can be tuned. For example, say in a particular topology I would want a higher IIP3, so I would set the value of alpha 2 to be higher, and in another case, say I need the power dissipation to be minimized, so I would set the alpha 5 value to be higher. Now this is the schematic of the noise cancelling LNA that has been used. This is the common gate stage, and this is the common source stage. This is the small signal analysis of the noise cancelling LNA. The S11 expression is Zin minus Rs by Zin plus Rs. And the condition for noise cancellation is as follows: GM1 R1 should be set to GM2 R2, and this must be initially enforced by the designer at the time of designing the initial netlist. The code cannot handle this condition all by itself. The third one being the gain expression. The gain expression is V out by V in is GM1 R1, which is also GM2 R2, and this is the expression for the noise figure. Now these are the update equations. If the gain loss is greater than 0, you increment both R1 and R2 by equal amounts. If noise figure is greater than 0, loss is greater than 0, you decrement R1 and R2 by the same amount. If IDD loss is greater than 0, you increase the multiplier of the MOSFETs by an equal amount. If the S11 loss is greater than 0, then you update the multiplier of the common gate device by this factor. Again, this 20 and 5 have been picked arbitrarily. Any other values can also be picked. These are also hyperparameters that can be tuned. IIP3 loss is greater than 0, then you decrement the multipliers, and alpha 1, alpha 2 and alpha are all tunable hyperparameters that can be changed as the need case may be. And also additionally, this increment alpha 1 and alpha 1 need not necessarily be the same. You can increment by different amounts and the code will still work fine. Now I'll just briefly describe the specifications. The noise cancelling LNA specifications are at 1 GHz and they are as follows. The gain needs to be greater than 15 dB, the noise figure needs to be less than 5 dB, S11 needs to be less than 10 dB, and IIP3 needs to be greater than 10 dBm. And this is the initial starting netlist. The parameters have been picked such that the input impedance is around 50 ohm. And as you can see, the AC gain is around 15.8, power is around 1.19 milliwatt, noise figure is around 5.1. The noise figure spec is not met. S11 is around minus 17.54, IIP3 is around minus 7 point something dBm, and loss is 2.1. After running for around 100 iterations, this is the best netlist. The power consumed is slightly higher, 1.8 milliwatt. This is fine because in this case the higher weight was given on the IIP3 spec, and the AC gain is around 18.93 dB. Noise figure is around 2.79. Now it has met the spec. The S11 is around minus 13.81 dB, and the loss is very low, 0.002. Now I'll just run the code for 3 iterations in cadence. So this is the schematic that has been built for the noise cancelling LNA. So now I'll run the code. as you can see, the code is running. Several files have been created. So as I had shown the initial netlist parameters, these are exactly the same things that have been printed out. The loss of 2.1. Here I am running it only for 3 iterations due to time constraint. However, in the report I have mentioned the entire procedure for several other netlists as well. And this is the best netlist after 100 iterations, as I am showing here. Now, as I told earlier, based on a certain threshold which this netlist satisfied, there was a PVT variation check, a sensitivity check and a mismatch check, all of these which have been run, and that analysis also I will demonstrate after this netlist has been successful. And as you can see, in 3 iterations, the loss went from 2.1 to 2.03 to 1.96. The loss is going down. Now I will run the sensitivity related checks on. Now, as I told, we will run PVT and sensitivity checks on the best performing netlist. As you can see, the analysis has just started and this will take some time to run. We will just wait for the first loss to be printed, the first or the second loss, and then we will move forward. As you can see, the loss at minus 40 degree has been printed. This loss takes into account some 1% mismatch between the actual values and the predicted values also while computing the loss. We will wait for the loss at 0 degree centigrade. As you can see, the loss at 0 degree centigrade has also been printed. The temperature analysis is done at 4 different temperatures: minus 40 degree centigrade, 0 degree centigrade, 27 degree centigrade and 100 degree centigrade. The process variation is done for 5 different processes: top TT, top FF, top FS, top SF and top SS process. And the voltage supply variation is done at 3 different voltage supply values, that is at 0.81 volt, 0.9 volt and 0.99 volt. This is because for the TSMC 28 nanometer technology, the voltage supply is nominally 0.9 volt and the sensitivity is done only at the right side sensitivity, that is, you increment every parameter by 1% and see what happens. That is the right sided sensitivity that has been analyzed. And the temperature sensitivity has also been analyzed, that is, you increment the temperature by 1% and see how the circuit parameters change. As you can see, the temperature analysis has successfully completed for the noise cancelling LNA. Now the process variations happens. This will take some time to run. In the meantime, I will continue. So this is the loss of the noise cancelling LNA as a function of number of iterations. This is over 100 iterations. As you can see, the loss smoothly goes down for the noise cancelling LNA. Now we move on to the resistive feedback LNA. This is the schematic that has been used. These are the small signal expressions. The S11 expression is the same, that is Zin minus Rs by Zin plus Rs. And the looking in impedance is 1 over GM1 for a large RF, which has been assumed. And the gain expression comes out to be 1 minus GM1 RF by 1 plus GM1 RF, which can be approximated as minus RF over Rs for large RF. And the noise figure expression is this. Moving forward, again, if the gain loss is greater than 0, you increment the resistor and the multiplier of the MOSFET M1 by an equal amount. If the noise figure loss is greater than 0, you decrement the value of RF. If IDD loss is greater than 0, you increment the multipliers of both the MOSFETs. If S11 loss is greater than 0, you increment the multiplier of the MOSFET. Again, this number 20 and 5 are not some very special numbers. These can be picked as the need be. If IIP3 loss is greater than 0, you decrement the multipliers of the MOSFET. These are the update equations. And again, alpha 1, alpha 2 and alpha are all tunable hyperparameters that can be chosen according to the need. And also, as a note of caution, this alpha 1 and the alpha 1 used in the linear combination of the loss are not the same. They are completely different. This alpha 1 is completely unrelated to that. These are just notational convenience that I have used here. And these are the results for the resistive feedback LNA. I won't be specifically showing this due to the time constraint on the video. So this is the starting netlist. The starting netlist has an AC gain of 9.11 dB. Just a minute, I'll briefly describe the specifications of the resistive feedback LNA. The resistive feedback LNA has the following specifications. They are defined at 1.58 GHz. The gain needs to be greater than 10 dB. The noise figure needs to be less than 4 dB. The S11 needs to be less than minus 10 dB. The IIP3 needs to be greater than minus 15 dBm. And this is the initial netlist. It has an AC gain of 9.11 dB, which does not meet the spec, by the way. The noise figure starting off is 4.8 dB, which is again not meeting the spec. The S11 is minus 12.93, which meets the spec. IIP3 is minus 10.35, which meets the spec. The loss is 1.68 and the power dissipated is 1.28 milliwatt. In this case, while running the code, there has been higher weight given to the power dissipation. So thus you can see the power dissipation has gone down from 1.28 milliwatt to 0.8 milliwatt. The AC gain has gone from 9.11 dB to 12.79 dB. The noise figure has gone down to 3.69 dB. The S11 now is minus 20 dB and the IIP3 is minus 14.26 dB, and the loss is extremely low, 0.000942. This is the best performing netlist. Again, on the best performing netlist, these checks were performed: the temperature analysis check, the process analysis check, the voltage supply analysis check, and the sensitivity check. And as we speak about this, let's check what is the status. This has successfully executed. As you can see, the temperature analysis is shown at the top, then the process analysis is shown next, then the voltage supply analysis is shown next, then the sensitivity is shown. Sensitivity is the change in the loss when the component parameters are perturbed by 1% to the right, and temperature sensitivity is the change in the loss once the temperature is perturbed 1% to the higher end. So this is the demonstration which I wanted to show in cadence. Now I'll move on to the presentation. Over 100 iterations, the loss function of the resistive feedback LNA varied like this. As you can see, initially the loss goes down and then it takes a spike upward and then roughly remains flat for some time and then again starts decreasing and then it again starts increasing. Each of these are a point of minima which we can consider, but considering the loss constraint we have, I have picked this netlist and it performs the best. Statistics that were obtained. Both the netlists were run for 100 iterations. The number of netlists that passed the initial gradient descent and satisfied the loss below that certain threshold in the noise cancelling case was 68 netlists, and in the resistive feedback it was 12 netlists. The bound was more stringent in the resistive feedback netlist, as you can see, and the number of netlists that passed the PVT variations in the noise cancelling LNA was around 32, and in the resistive feedback it was 3. The number of netlists that passed the sensitivity check finally in the noise cancelling LNA was 10, while in the resistive feedback it was 3. The lowest loss obtained in the noise cancelling LNA was 0.00199, while in the resistive feedback case it was 0.001, and the sensitivity in the noise cancelling case was 1.392 into 10 power minus 5, and for the resistive feedback it was 1.629 into 10 power minus 5. These were some key statistics that were obtained during the run of the algorithm. Moving forward, now I'll describe the best netlist that was obtained for the noise cancelling LNA case. The specification for gain was 15 dB, noise figure was 5 dB, S11 minus 10 dB, IIP3 minus 10 dBm, power needed to be minimized. The starting netlist had a gain of 15 dB, noise figure of around 5.1, and S11 of around minus 17.53, and IIP3 of minus 7. Power was 1.32 milliwatt, and the loss was 2.1. The final netlist had a gain of 18.85 dB, noise figure of 2.9. The S11 came out to be minus 14.5 dB, IIP3 of minus 5.2, and power of 1.79 milliwatt, and the loss is significantly low, which is 0.00199. In this case, as I described previously, the emphasis was given on IIP3 and noise figure. Thus, the power has slightly increased, and the sensitivity was evaluated to be around 1.392 into 10 power minus 5, while the temperature sensitivity evaluated to be 2.04 into 10 power minus 7, and the time taken to run this was about 35 minutes for the normal gradient descent optimization for this case. And now we come to the resistive feedback LNA. The gain spec was 10 dB, noise figure was 4 dB, S11 minus 10 dB, and IIP3 minus 15 dBm. The starting point had a very low gain, 9.11 dB. It does not meet the spec. So does the noise figure, which is 4.80 dB. S11 of minus 12.94, IIP3 of minus 10.35, power of 1.288, and loss of 1.68 were the initial starting points. And the final result, the gain came out to be 12.11 dB, noise figure of 3.8 dB, S11 minus 18.87, IIP3 minus 13.43, power of 0.95 milliwatt, and loss of 0.001. In this case, the emphasis was given on power and noise figure. That's why the noise figure came out to be much lesser, and the power also decreased significantly. The sensitivity evaluated to be 1.6 into 10 power minus 5, while the temperature sensitivity evaluated to be 5.3 into 10 power minus 7. The time taken to run this code was about 30 minutes. And as you can see, in the noise cancelling LNA, the starting point was much better compared to the resistive feedback LNA, though the loss is less, because more specs are almost met in this case compared to this. Moving forward, the conclusions are as follows. The role of a designer is crucial and cannot be replaced. This automation makes the design process only faster and easier to reach the local optimum. Again, we cannot guarantee reaching of global optimum. It reaches only the local minima for sure. The local minima highly depends on the choice of initial netlist. The better it is in relation to the optimum, the faster it converges. The key drawback in this type of automation is that the code cannot generate netlists of its own. It makes the existing ones better. With that, I would like to conclude. Thank you.